Okay, organic chemistry part 2. This is round 2 on our acids, bases, and our mechanisms. I love it because I'm really excited that this is recording and that we're able to work our way through this so that you can maybe stop and pause and take a coffee break or take your notes, and definitely use colored pencils and things like I am. I love it. All right, so let's go through a little bit more. So we just hit our Arrhenius acid and bases and drew a mechanism. Isn't that fun? And now we just hit a Bronsted-Lowry base and reviewed that definition. Okay, I love it. We have a third. So let's get even more modern. Again, our Arrhenius acids and bases, well, son of a motherless goat, they've been around forever. That definition has been around forever. And then as we get a little bit more modern and we realize, wait a second, there are other compounds out there. They don't have to have an OH. That could be a base. Well, then we evolved into that Bronsted-Lowry definition. And now we're going to hit even a third, more modern definition, and that is something called a Lewis acid, Lewis base. So let's look at a Lewis acid and a Lewis base and see how that definition changed again. So I'm going to add a reagent. I'm going to stay with ammonia. And you notice that I am drawing out those structures. When you first start acids and bases, you're going to want to simplify in your heart, and you're going to just want to draw NH3 and just wing it. But it's going to really help you to draw everything out so you can actually track your electrons. And then I'm going to add a reagent that we likely drew in Gen Chem 1 and then never thought about it again. But it's actually very, very common as a Lewis acid. So I'm going to take a boron species. We can have all kinds of things on our boron. I'm going to start the most basic with BH3. And what's different with boron is that you actually only bond with 6 electrons. This was one of our exceptions to the octet rule back in the day in Gen Chem 1. Now you may not remember that. It's probably been a little while since you saw it. But what it means is basically boron has this empty space. It has an empty orbital, and it's only got 3 electrons around it, which means it can only really make and share with 3 other atoms, but you have this empty space. So it doesn't get any more positive than that, right? If you've got empty space, you've got this big positive empty hole there. It's not quite charged. This is neutral, but you've got empty space there. And then with your nitrogen, we saw in our last example that these electrons are actually quite available. You've got a nice available lone pair. So in our Lewis acid and Lewis base, you'll notice in the acid that we're about to react to the empty space, not the hydrogen. So is this really an acid? It is. It's just a different type of acid. For a Lewis acid, you are filling in that empty space. You can accept a lone pair. With a Lewis base, you're using a lone pair to form that bond. So let's draw the product, and then we will draw the definition. Okay, you still have your ammonia. You just reacted with that BH3, and we formed a bond between these two. So you're now sharing a little bit more than normal in your nitrogen, and holy crap, you've now got a little bit extra in your boron, and we just made a salt. Again, no water present. So then what's the definition for a Lewis acid and a Lewis base? A Lewis acid can accept a lone pair, and a Lewis base can donate a lone pair. Now, you may or may not have learned your Lewis acids, Lewis bases, but we will use them quite a bit this semester. They're all important. We're going to use every one of these definitions this semester. So these are our common definitions of acids and bases. I am going to include a fourth definition. Oh, I need to give myself just a little bit more space there. Okay. Number 4 definition. It depends what you're mixed with. At the end of the day, we are going to scramble all kinds of stuff and mix it together. And what really determines what's an acid or a base is really what you mix together and which one's stronger than the other. I'm going to challenge us by the end of this semester. We're going to have 2 acids you've been taught are very strong acids. Well, when you mix them together, one's stronger than the other. So one's an acid and one's a base. So if this is the definition that we're really going to use, how in the world do you know what you have? Well, this is where we're going to use a pKa table. We're going to have a series of things to look at. We are going to look for available electrons always. We're going to work through a list. How can you have available electrons? You can have a negative charge. That one's obvious, right? Or you can have lone pair. And then we're going to look for, could be available H+, so a partial positive on a hydrogen. And how do you figure any of this out? We're going to draw structures and use a pKa table. So I've included the one link on this paper is this Mastering in Organic Chemistry because I'm using this pKa table. I've also included another pKa table that's an educational copy from a textbook. So both of these have been taken from someplace. You definitely want to get your hands on a pKa table. And what does a pKa table tell us? Let's start with our structure and some pKa numbers. And let's do a little bit of a review on why we look at pKa and what pKa even is. So let's say I take something like HCN and ammonia. Okay, both of these are not technically on our Strong's list. So if you had a good Chem 2, you took strong acids and strong bases and set them aside. Everything else was a weak acid or a weak base, and you put those in an equilibrium reaction. Okay, so the reason we use a Ka then is that we're judging how much this reaction happens. So it is literally a ratio of your products over your reactants. And what would our products be in that? Let me give it away for free and then we'll draw it. Okay, it would be, okay, so your Ka is giving you this relationship. If that reaction's pretty good, you're going to have a big number here. If that reaction kind of sucks, you're going to have a big number here. So if that reaction is pretty good, that means you have a high Ka. That means you've got a pretty strong acid or base combo. But since we're looking at Ka, we're looking at the acid. So it's a nice comparison to picture HCN in water is what you would do in Gen Chem. And you would compare your Ka to water. You would take your Ka and see if it's greater, then it's an acid. Then it's acidic. If your Ka is less, then it is basic. So the only difference for us is we're not always going to compare to water. So our Kas are going to tell us which one wins. If your Ka is higher, that's your acid. If your Ka is lower, that's your base. Now, typically for organic, however, we go ahead and make the transition. We take our Ka and we convert it to pKa. Because we can tell from our numbers which one's the acid and which one's the base, we tend to just use the pKa. So let's look at that relationship. pKa is, again, the inverse log, or the negative log, not inverse log, negative log of Ka. So we have the inverse relationship. So in other words, if your Ka is high, your pKa is low, and that's your acid. If your Ka is low, then your pKa is high, and that's your base. So let's put this into practice. Now I've given us several examples here for a pKa table. Let's go back to this initial example right here, HCN and ammonia. If you've never seen them before and you're going to mix them together, how do you figure out what you have? Well, let's find ammonia on our pKa table. There it is. And let's find a nitrile on your pKa table. And we don't have just HCN on this one, so let's look on this one. Okay, we've got two of them, so let's see if we can find HCN. There it is. Our pKa is 9.1. Let's see if we can find ammonia. Here it is. It's 36. Okay, so let's mix them and let's see what happens. All right, so let's take HCN and let's get in the habit that if you have a pKa, write it right underneath. What's our pKa? 9.1. Let's take our ammonia. What's the pKa? 36. Aha! Which one wins? All right, the lower the pKa, that's your acid. Our higher pKa, that's our base. Okay, you see where I'm headed. Once you know which one's your acid and which one's your base, we can draw our mechanism. So let's draw out our structure. Your base has to have an available lone pair. It does. Your acid has that nice hydrogen out there and available. So how do we draw our arrows? We always go from base to acid. We go from available electrons to that hydrogen that's nice and available. And then your mechanism lets you draw the product. We still have our ammonia. We formed a bond right here. And then what happens to your cyanide? You leave behind those electrons on carbon, and there's your salt. So my goal for you in this unit, by the time you take your acid base test, is for you to literally be able to take any kind of two organic compounds, mix them, and see what would happen in an acid-base reaction. That's our first place to start. So let's try it again. Let's try a sample. I'm just going to make up something. And I'm going to make up, how about this? All right, I'm going to guess that these are two reagents you've never seen before, let alone mixed them before. So I'm going to train you on definition number 4. What's the first thing we do? Oh, crap, we haven't seen them before. Let's see if we can find them on a pKa table. In fact, let me make this just a little bit nicer. Let me do this. Let me make that on our pKa table. Okay, so let's take these two and let's find our pKa. Are they even there? Okay, how do we find, do we have a triple bond? I see one here. That is at 26. All right, let's see. Let's write that down here. 26. Okay, and then how about that sulfur? Did we find that anywhere? Not yet. Not yet. Do you see sulfur anywhere? There it is. That is a 10.7. Okay. So if we just started here, and we tried to mix them, which one would be the acid? Lowest pKa wins. 26 means that's the highest one. That would be our base. But now what's awesome is we would discover this is a trick question. Why is this a trick question? Do we have available electrons? No, we do not have a negative and we do not have a lone pair. So this would be a fun trick question. Okay, so our pKa table, we're always going to start there, and then we're going to find our available electrons. And in this case, we had a nice tricky one. But we're going to spend the next video just literally applying this and adding vocab. We're going to get to know our pKa table. We're going to do a bunch of examples, and we're going to go backwards and forwards. So let's stop this video, and then we're going to shoot another one doing the same thing and just